corollaries. This is just one. This says the following. So let f from u to Rn. So u is again open set in Rn. Be C1 if f dash x. Now I make the assumption that the derivative is invertible at every point in the domain. If f dash, oh, sorry, not 0. It's opposite of that. If f dash x is invertible at every x in U, then the statement is that the image of this open set is open. So recall that the inverse function theorem said the assumption was that the derivative is non-singular or invertible at one point. Then we were able to find a neighborhood around that point, open set around that point, and the image point, such that f was 1-to-1 and on-to and so on. Here, nothing is being said about 1-to-1 or on-to. I mean, of course, f of u, f mapping u to f of u will be, of course, on-to, but no statement is made about 1-to-1 or anything. It's just that the image is open. And why is this true? Well, so what we can do is, for every x in U, the inverse function theorem gives an open, let me call it W subscript X contained in U, which contains X, and all that matters for this corollary is that the image of this smaller open set Wx is open in Rn. So this is our U, this is F Rn. For every X, in fact, it was an open ball that we got. So this Wx, this was Wx. F of Wx is an open set. So that we have for every X. Now what, and this each Wx is in U. So U can be written as the union of all these Wx's, X in U. So when I take f of U, I'll be just taking the images of all these Wx's. Each one, f of Wx is open, and we have a union. So here the general statement is, if you have an arbitrary union of open sets in a metric space, it's open. So I'll leave that for you to check. If XD is a metric space, you have to be, when dealing with open sets, you have to be careful about intersections, but unions are fine. So arbitrary intersections of open sets, of course, need not be open, but arbitrary unions are. If XT is a metric space and UX in X U alpha in X is open, alpha in some index set, then if you take the union of all these U alphas, is open again. So just go through the definition of open set, that's all. Take a point in the union, you're supposed to find an open ball, etc., and you can so easily check that this is open. So the point is that the inverse function theorem gives an open set around each point whose image is open, but the whole domain can be written as a union of the small open sets, and therefore f of the whole domain is union of f of the smaller open sets, etc. All right, so that's that. Now I'll move on to the second important theorem. So this is actually something that one sees more often in, especially in applications of this inverse function theorem. Rather than the inverse function theorem itself, one sees this one, implicit function theorem, because as you'll soon see, it has a very concrete form about solving some equations. And as we know, in every application of mathematics, ultimately it boils down to solving equations. So this one, the setting is also rather simple. Rather than talk about some function being one-to-one or the image being open, here we address this simple-minded question. Suppose, let's start from R2 to R. I have a function, I have a function from R2 to R, and I would like to look at this equation f of xy equal to 0. So an example to keep in mind, I mean anything will do, but here we'll need this example, x squared plus y squared minus 1. So notice that here f of x, for this particular example, f of xy equal to 0 amounts to saying that x squared plus y squared is 1. So in other words, x and y lie on the circle. Unit circle with center 0. Well, what we want to ask is, suppose we know that f of AB is 0 for some AB. Can we find x equal to g of y so that f of gy comma y is 0 for all y close to b. So in other words, I have one solution which I have somehow found out. But what I want to know is, so this solution f of AB is 0. Now, if I change this b slightly, that's what y close to b means. So if I change b slightly, then will I still be able to find another solution? So I want to get another a, so that for the new b, I'll still have f of a prime b prime will be 0. That's what I call g of I. In its most simplest form, this is the question we are asking, but we want something more actually. We will be able to say something more under some condition on the derivative of f. We'll see that we get the answer to this is yes, and not only that, this g will be depend nicely on X, G will be depend nicely on Y. So G will be a continuously differentiable function of Y if F is so. And why is this called the implicit function theorem? That should be clear enough. After all, I mean, we are just solving for, we have an implicit equation for X and Y. Involving X and Y, and we are solving for X in terms of Y. X equal to G of Y. Now, I mentioned a condition on the derivatives. Why is that even necessary? So for that, look at that example. F of xy is x squared plus y squared minus 1 equal to 0. Now, as we know, the set of all xy for which this holds is just the unit circle. And suppose I take a specific point. Let me take the point AB equal to this point 1, 0. This is my AB. Well, you see the problem here. If I want to get x equal to actually I want it the other way. I don't want AB equal to 1, 0. Well, we'll see. Del F by del X is at any point it's given by just 2x. Yeah, I want it, no, not 1, 0. I want it here. Sorry, not this. This is not AB. AB is here. 0, 1. Now you see the problem here. The problem is that the solution, if I here is, it cannot be written as a y. I cannot get x equal to g of y, because for a single y there are two possible values of x. So for, if I am on the upper hemisphere, for every x, for every y, I'll get two possible values of x, however close you are to this 0, 1. And the reason is that this thing is 0 at AB equal to 0, 1. X is 0 essentially. So because of this, you run into problems solving this equation at this point. But it turns out that that is the only problem, that the some derivative vanishes. Now, what exactly, which derivatives we are supposed to look at and so on, that will be what we'll look at. And in Rudin, if you look at Rudin, the as I've been repeatedly saying, the main idea behind many of these theorems will be is that differentiable functions behave like linear transformations. So in fact, Rudin does the case of linear transformations to see what is going on. By the way, the more general question is, more generally, we deal with f from Rn cross Rm to Rn. Again, we look at an equation of this We want to solve for x in terms of y under two conditions. One is f of AB is 0. Second one is a condition on some derivatives of f. What that condition is, we'll have to see. It already gives the previous example gives a hint. That the condition should be that the partial, if I look at just the derivative of f, only the x component, that should be invertible, and that should be, in fact, that turns out to be enough. So let's look at the case of linear transformations. The case of linear f. So here I have a linear transformation Rn cross Rm to Rn. So this is Rn plus m. And here the coordinates I will write as xy, x comma y. More explicitly, it will be of this type. By the way, in case you get confused about, there are two things here, Rn, n, m, n and m. In case the domain is going to be Rn cross Rm. In case you get confused about the target being n or m, just keep in mind that what are we solving for? We are solving for x in terms of y. So the unknowns are n variables. Since x is in Rn. And therefore, we want the equations also to be n equations. So the target should be in Rn. So just keep in mind that the number of unknowns and number of equations should be the same. That will immediately tell you that the target is Rn. Okay, so this, okay, fine. Now it's all right. This case will be, as usual, trivial. I mean, the condition that we want will become clear. So what we'll do is we'll define two things here. Let Ax from Rn to Rn be Ax acting on H equal to A of H comma 0 for all H in Rn. And Ay from Rm to Rn be Ay acting on K is equal to A of 0 comma K. For all K in Rm. So all I'm doing is I'm just restricting this map. So this is Rn. Schematically, think of the x-axis as Rn, y-axis as Rm. And we have two subspaces, Rn sitting here as the x-axis, and the y-axis it's also a subspace, Rm. I'm just restricting the big map A, which is defined on this whole thing, to these two subspaces and calling them Ax and Ay. So in terms of these, the overall map boils down to A of Hk. I can write as A of, by linearity, AH0 plus A0k. So this is what we call AXH plus AYK. Well, so the statement for, and remember, we are interested in the equation A of hk equal to 0. We want to solve for h in terms of k. That's the goal. The way we have written it in this form, it immediately becomes clear what condition we need. So if A belongs to, if A is a linear transformation from R n plus m to Rm, Rn, and if Ax is invertible, then for every k in Rm, there is a unique h in Rn such that AHK is 0. In fact, we can easily write down the formula. H is equal to minus Ax inverse A by K. And the proof is a triviality. We had AHK equal to AXH plus AYK. And if I set this equal to 0, then AXH will be minus AYK. Now, the assumption is AX is invertible. So, which implies H is minus AX inverse A by K. That's it. So, this is a completely trivial statement actually, but this gives an insight into what condition we need. The condition is that this AX is invertible. Now, how should this help us in terms of general differentiable functions? Well, how does this whole stuff about thinking of functions as differentiable functions as linear transformations is essentially via the derivative. So what this suggests is that the derivative of f, that's A, the derivative should have the property that when I do this AX business, that should be invertible. So in fact, that's the theorem. So whatever happens for the derivative happens for the function. That's the philosophy. So let f from E to Rn, E is a subset of R n plus m, open. So let this be C1. Suppose f of AB equal to 0 for some AB in E. Let A equal to f prime AB. And assume that this is the main point. Assume that AX, this previous example of linear transformation immediately suggests that what we need is AX is invertible. Then we should be able to solve the equation f of xy equal to 0. you should be able to get x as a function of y, so that that equation is solved, at least locally. Then there exist open sets U in Rn plus M and W in Rm with AB in, oh, of course, this U should be in, yeah, you should be in E with AB in U and B in W. See, this W thing is just supposed to deal with the Y variable part. This U deals with is both X and Y, such that for every Y in W, there is a unique X with XY in U and f of xy equal to 0. So this basically deals with the solving the equation part. We can, if we know that, so it's exactly what I said earlier. But now I come to how this solution x as a function of y depends on y. So that's if we let x equal to g of y. So in other words, if we define a function g by this, then g from W to Rn is C1. Of course, g of b is, no, not of course, g of b is 0. The of course part is this one, that the main defining property of g is that it's a solution. So g of y equal to 0 for all y in W. And we can also say what the derivative of g is. At least the why we make any statement about the derivative is, as usual, this is an existence theorem. It says that there is some we can solve, but it doesn't tell us how to find g. The best we can do is we can say something about the derivative of g.
So isn't g of b equal to a?
G of b equal, oh sorry, yeah, g of b equal to a. Yeah, you're right. That's absolutely correct. G of b equal to a. And the only thing we can say about g is that at least we can compute its derivative at the point b. Beyond that, we don't have an explicit formula for g, but since we know its derivative at b, at least we have some first order approximation of g. That's the hope. So this is minus, just like the linear transformation case, minus ax inverse ay b. That's it. So this is the statement. Now let's see how far I will be able to. I won't be able to complete the proof, but that's okay. So this is an important theorem. So let's, in fact, even before I begin the proof, concretely, let's see what this says. Concretely meaning in terms of coordinates. We have a bunch of equations f1 xn y1 ym equal to 0. And there are n equations. And you are supposed to think of this as n unknowns. The x1, x2, xn are unknowns. For given y1, y2, ym, I'm interested in finding out x1, x2, xn. So n unknowns, n equations. So at least that matches, but that's not enough. So the two main conditions are if one, f of a1, an, b1, bm equal to 0, f1, fn, a1, an, b1, bm equal to 0. This is one condition. The other one is the derivative condition. So d1 f1, d1 fn, dn f1, dn fn, ab is invertible. So this D, capital D notation is just a shorthand way of writing the usual partial derivative. D1 F1 is just del F1 by del X1, etc. So this matrix of partial derivatives, notice that this is a square matrix. The original F is, if I take its derivative, it's a mapping from linear transformation from Rn plus m to Rn. So the matrix will not be square, but I'm not looking at the full derivative of F. The point is, I just stop at Dn. F has more variables in it, n plus m variables, but I just look at the first n variables, take partial derivatives of that. This matrix. Now, you might wonder what this matrix has to do with the condition in the implicit function theorem is this AX is invertible, where A is the full derivative matrix. I leave it to you to check that this AX, if I have this matrix and if I look at the matrix of AX, it is just a submatrix of the full matrix and it's given by just this. What I wrote here, this matrix. Check that this matrix represents or is the matrix of represents AX, where A is the full derivative.
So what is AX in the original statement? It's not like
AX is that, no, AX is when I discuss that linear transformation example, if I have a linear transformation from Rn plus m to Rn, AX will be from Rn to Rn, and it's just AX of H is A of H comma 0. It's just the restriction of A to the subspace Rn sitting inside Rn plus m.
okay.
So I defined this when I talked about the case of linear transformations. AX and AY. Though what is relevant here is just AX. So with this definition, you can immediately see, I mean, it's nothing to do with derivatives. For any linear transformation, the matrix of AX can be easily obtained from the matrix of A by just it's a certain submatrix. You just have to identify which part of it. And for the derivative, you get this. So this is the concrete version, which you'll see if you look at a physics book or engineering textbooks and so on. The implicit function theorem will be stated like this. It's the same thing as the more, what we stated. Well, I'm not actually just stated the hypothesis. What is the conclusion? The conclusion is, if those two conditions are met, then the system of equations not this, here actually, this, if we call this star, if these two conditions are met, then star has a unique solution for every y near B. And this solution, unique solution, I mean, it's a bunch of solutions, x1, x2, xn. And this, if you put them together, what I'm calling unique solution, this solution depends in a continuously differentiable manner on y if f is C1. That's it. If f has continuous partial derivatives, the solution will also depend this. So it's a non-trivial theorem because you can easily write down several implicit equations where it's almost impossible to solve directly. So this theorem says that all you have to do is find one solution, one numerical solution at one point, and then you have to check a derivative condition, which is quite easy to do. Then you are guaranteed that the original implicit equation has a solution. But it doesn't tell you what the solution is. And that's, of course, impossible. Right. So let's, in fact, okay, so let me begin let me see how far I can go. I'll just set the framework. So the idea is, I mean, after all, this is supposed to follow from the inverse function theorem. But the main difference between the inverse function theorem and this is that, of course, the statements are all different, but abstractly, there you had a function whose domain and range are both in Rn. Here you have Rm plus n to Rn. So what we do is we are going to define a function. Remember, this E was an open subset of Rn plus m. Now I'm going to make the target also Rn plus m be f of xy equal to the original f of xy, which was in Rn, and this y, the input variable y is in Rm. So I'll put the same thing here. It's not completely arbitrary. Just I'm not putting y just to get the dimensions the same. It's the most natural thing to do, as you'll see in the proof. So there are other choices for putting something here, but y is the simplest one. So I have this. So I would like to play around with the implicit inverse function theorem. For now that I have an open, I have a function from Rn plus m to Rn plus m. I'd like to see what the inverse function theorem will yield. But right, so for that I need to know the derivative of f at the point AB. So let's see what this is. The claim is that this f prime AB is invertible. The derivative is invertible. Only then can I do something. Now, yeah. Again, if you want to calculate f prime AB as a matrix, it's quite easy. So in fact, it will be a block matrix, and one can directly see that this is because the second stuff that you're putting there will, when you differentiate it, will just yield the identity matrix as a block. But let's do it in a slightly abstract fashion without using the matrix. The way Rudin does it is as follows. So first, so let's look at this f of a plus h, b plus k minus f of ab. Well, this is just go by to the definition of capital F. So I'll get, now the point is the y slot in the first term will be b plus k. In the second slot, so, okay, I'll just write it out. F of a plus h f of a plus h, b plus k, comma, b plus k minus, now this will be f of ab, comma, b, but f of ab is 0 by assumption. So this will be f of a plus h, b plus k. There's a b plus k here and a b that cancels out, so I'm just left with this. So now, yeah. Now, let's expand this f of a plus h, b plus k minus f of ab. By definition, this is f prime ab acting as a linear transformation, acting on hk plus r of hk. So I'll write that again. F of a plus h, b plus k minus f of ab is f prime ab acting on hk plus r of hk, where this half the screen is red for some reason, where the main property of this remainder term is that R of Hk by norm Hk, this should go to 0. By the way, who's recording this? Because I forgot to press the record button. So if you have recorded this, please send it to me. Is someone recording this?
I think it's always just saved on Teams.
It will be saved on this channel. It will be available here.
No, but it has to be recorded. Otherwise, it won't be saved, right?
As of now, I do see it as recording. 51 minutes of the meeting has been recorded.
Yeah, but I didn't press the record button, but is somebody else recording it is my question.
Yes, I pressed it, but it'll be available to everyone on the team.
Oh, I see. You pressed it. Okay, very good. Okay, fine. Oh, that's very convenient. So anybody can download it. Okay, fine. So now, right, where was I? A plus H, yeah. So this remainder term, so, and this again, so this is 0 anyway. So I had this, and so I'll just use it where was, yeah. I was interested in capital F, and I'm left with this expression here. So I'll just use the stuff there. Therefore, f of A plus H, B plus K minus f of AB equal to, now whatever I had, I'll just put f prime AB HK plus RHK. Oh, I'll split it into two parts, K plus the other thing is RHK K. Now this immediately tells me that the point of writing it like this is that I can immediately read off the derivative from this. So the remainder term for the small f was this RHK. And it had the main defining property of this term is that when I divide by norm of HK, it should go to 0. Here, one guesses that the remainder term is this thing here. So when I divide this by, divide this by norm of HK, well, not quite. No. This is not quite what I want. Let me see. Oh, no. Actually, yeah, I can't use, I already used the K here. So here I'll put 0. Yeah, that's right. So there was only one K in the seconds. I put it along with that. So this is the remainder term. So this has the property that when I divide by norm HK, it goes to 0. So this tells me that since RHK, K divided by norm HK, limit HK going to 0 is equal to 0, we can say that by the definition of the derivative of capital F is given by this expression. This is the linear part of this difference. So we can say that we see that capital F prime AB acting on HK is just given by F prime AB acting on HK, comma K. So, and we were saying we wanted to claim that the derivative is non-zero, capital F. So we just have to see that the kernel is trivial. So if this is 0, if f prime AB HK is 0, 0. Then we'll get K equal to 0 here. This term is 0, this term is 0. F prime AB H, 0 is also 0. So this is f prime AB H, 0 is the same as AX H is 0. By definition, this is what it is, which implies H is 0, since we assumed AX is invertible. So actually, this makes it seem a bit more complicated than what it is. It might be a good exercise for you just to write down, starting from this expression, just write down the derivative matrix for this capital F. You will get 2 blocks. And from that, you can immediately see that. And one of the blocks is the derivative of small f. You can immediately see that at AB, that block matrix will be invertible. That's a very direct way of checking this statement here, this claim. So this is a good place to stop. So let's stop here. On Wednesday's class, I'll resume rather than post another lecture on this. I'll do this in Wednesday's class. By the way, is it? Would you prefer that I do these proofs in real time, or it's the same thing, I guess, or I just post it? Which one do you prefer? Anyone?
Sir, if you want to get the general opinion of the batch, we can set up a poll and ask people what they like. Personally, I kind of prefer the live version, but I do understand that time constraints wise, a recorded version might be better for some people.
Yeah, and also, unlike a real class, there's no back and forth here. Occasionally, you do ask some questions, but not too many. So practically speaking, there's not much of a difference. It's another matter if every now and then people were asking questions. But that's not happening here due to various reasons. So I guess there's not too much of a difference. By the way, feel free to make any, not just this question, in general, since this is all a new experience for all of us. Feel free to make any suggestions in the post. In fact, what you said, take a poll is a good idea.